Hello and welcome to the second episode of the Calculus 1. I am Mohammad Momezadeh, the presenter of this lecture. So previously we discussed about the concept of the function and different type of the presentation that we can consider it for a function. So in this lecture, as we promised before, we will discuss about the exponential function and the property of logarithm, and also we will discuss about the trigonometric function, two important concepts that later on we will use that one in our discussion. So this part of the actually course can be considered as a prerequisite of calculus. It's not the main part of the calculus, but it's totally essential to understand the concept of the derivative, integral, and so on. So we will start our discussion by talking about the exponent and some rules of the multiplication of exponent and logarithm as well. So let us take a look at the first slide. So as you can see over here, we will start our discussion by the concept of the exponent, and at the beginning we should know what is the meaning of x to the power of n. So when we discuss about x to the power of n, when n is a natural number like 2, 4, 5, something like that, means that x should multiply by itself n times. So it means that we multiply x by itself n times. So let me just mention over here that n times we multiply the x by itself. So if we consider, for example, the number like 4 to the power of 3, that we call it 4 cube, means that we should multiply 4 by itself 3 times. So it's going to be equal to 4 times 4 times 4. 3 times I multiply 4 by itself. In the meantime, we have a deal over here that if x has an exponent of actually 0, then x to the power of 0 will be equal to 1, except that we have 0. 0 to the power of 0 is undefined. So 0 to the power of 0, as I said, it is undefined. We cannot define that case, but for the remaining part, if we have a number, then for example e as a Euler number minus pi, which is an irrational number totally, to the power of 0 will be equal to 1. Any number except 0 to the power of 0 will be equal to 1. When we have the exponent, when we have some powers over here, the number over here is called the base, and this one is called the exponent or the power of that expression. So if we have a negative exponent, then we define the negative exponent as the inverse of that expression with the positive exponent. We need that type of the concept in a derivative too much. Means that when we have a negative exponent, you need to inverse that expression and put it with the positive exponent. So for example, if you have 4 to the power of minus 2 and you want to calculate it, when you have a negative exponent, you should inverse that expression. Means that you will write it 1 over 4, then you just put the positive exponent instead of the negative, so it will be 1 over 4 square. Indeed, when you have the exponent over there, by inversing the terms, you can have the positive exponent or the inverse number of the exponent over there. So over here, it's very important to mention that we can convert the number like that, and these rules that we put it over here is totally created based on a rule of the exponent that later on we will talk about it. So number 4 over here determine the fractional exponent as well. When we have x to the power of m over n, when we have also the rational number as an exponent, then to evaluate that expression, you keep the numerator for that number. Means that we have x to the power of m, and that n at the denominator comes to the roots of that expression. Means that it's coming to the roots of that expression. So we have x to the power of m with the n roots. For instance, if we have 16 to the power of minus half, if you want to calculate 16 to the power of minus half, then first of all the exponent is negative. To make it positive, we should invert it as we said it in a part 3. So we have 1 over 16 to the power of half. Right now, because we have the actually fraction in the exponent, then we keep the numerator for that number, means that 16 to the power of 1, and we put that denominator as a root. It's a square root or second root of 16. And when we have the second root, means that we are looking for some number that if we multiply 2 times by itself, it's gonna be 16. So for sure you can imagine that the number will be 4, because if you multiply 4 by itself, or 4 square will be equal to 16. So this is the number that we wanted. Or if we have 8 to the power of 1 over 3, if we want to calculate this one, then 8 to the power of 1 should be written, I mean the numerator keep for the number, and we have the third root of 8, and means that I'm looking for some number that if I multiply 3 times by itself, the result will be 8, and that number should be equal to 2. So you can see that the exponent, how the actually fractions at the exponent are working. So let me just erase the part that we have the examples and take a look at the rules of the exponent as well. So we have some rules for the exponent. For instance, x to the power of m times x to the power of n. If I have this expression, means that the bases of these two numbers are the same, but their exponent is different. Then if we multiply these two terms, we should add their exponent, means that the result will be x to the power of m plus n. So for instance, if you have actually numbers like an expression like x cubed multiplied by x squared plus x, then to calculate this expression you should multiply x cubed by the terms inside of the expression one by one, means that x cubed by x squared, x cubed by x. And if you multiply it, when you multiply the first term, because the bases are the same, so the result is x, and the exponent should be added. 3 plus 2 is equal to 5, because we have the multiplication of two numbers. For the second expression, we have x to the power of 4, because 3 plus 1 is equal to 4 as well. If we have a division in this situation, means that if we have x to the power of m divided by x to the power of n, this division can be written as a fraction as well, means that we can rewrite this expression as x to the power of m over x to the power of n. You can use the fraction demonstration for this type of the operations, and the result is x to the power of m minus n, means that we should subtract that one. Indeed, if you just take a look on this expression, you can take the result from the third rule of the actually calculation and a first item as well, because when we have x to the power of m over x to the power of n, this 1 over x to the power of n can be written as a x to the power of minus n, and the division can convert it to the multiplication, then use the first one to result this rule. So for example, if we have x to the power of 5 over x to the power of 5 plus x to the power of 4 over x squared, for example. If I have this expression and we want to simplify this expression, then you should divide each term one by the denominator. The result is x to the power of 5 over x squared plus x4 over x squared. Care about it, when we have a single value at the denominator, you can divide it like that. You cannot split the denominator on a numerator, so it can be happen only in this case. So x5 over x squared will be x cubed, because 5 minus 2 is 3, and x4 over x squared will be x squared, because 4 minus 2 will be 2. So this is the second rule of the multiplication. if the bases are the same, also we have the similar things over there. Means that if we have, for example, if we have x to the power of n multiplied by y to the power of n. Right now the bases are not the same, but the exponents are the same. So if we have this situation, the result will be x times y to the power of n totally. So for example, if I just give you some example by the numerical value, means that, for example, if we have 4 square times 4 cube times 3 square, for example, the result of this one will be equal to 4 times 3 or 12, and the exponent should be keep it for the number 12 square, which is 144. So we have the similar things for the division, means that x to the power of n divided by y to the power of n, where the exponents are the same, and we have a division. We can rewrite it like a previous case as a x to the power of n over y to the power of n, and the result will be the x over y totally to the power of n. The inverse part also is correct, means that if we have x over y totally to the power of n, you can split the expression and write it as a x to the power of n over y to the power of n. For example, if we have 8 cube divided by 2 cube, then to calculate that one, simply you can divide 8 by 2, which is 4, and the result can be written as a 4 cube as well. So this is the cases that we have it over there, and one of our most important thing is x to the power of n to the power of m. If you have two exponent, then you can multiply this exponent together, means that the result is x to the power of n times m. So you should multiply that exponent together to calculate the expression. For example, if you have 4 cube to the power of 7 then the result will be 4 to the power of 21. So you can see that by using that type of the actually rules, why we get the x to the power of 0 equal to 1 as well. So it's very simple to see over here that if we have, for example, x to the power of n over x to the power of n, then as you can see their expression are the same and the result should be equal to 1. But on the other side, if you use the concept of a division that we have it at this option, then you can rewrite that one as x to the power of n minus n, and this n minus n is as the same as x to the power of 0. So you can see simply that x to the power of 0 should be equal to 1. Because of that, we define x to the power of 0 as the value of 1. So right now we realize some expression over here, and let us recap all of them in one table. So I bring this table from the website of mathisfun.com. It's not a bad website. If you forgot something from the high school, you can find a lot of interesting concepts and definitions over there for the exponent especially, or the arithmetic cases. So you can see the law and example over here. As we said it before, x to the power of 1 is as the same as x. X to the power of 0 is equal to 1, and you can find the remaining expression that we had it over here, and all of them are gathered in one table. So let us take a look at the exponential function now. Before that we go forward, let us take a look quickly at the number e, or Euler number. This number can be defined as limit of 1 plus 1 n to the power of n when n tending to infinity. Means that right now we didn't discuss about the limit yet, but just keep a big number over here for n, and you can approximate or estimate the value of Euler number. Also, we can determine the value of the Euler number as 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial. and so on up to the infinity. And factorial, 3 factorial means that 3 times 2 times 1 and so on. This approximation leads us to the value of 2.718228, so on. This expression, this number is irrational. By the another words, there is no repetition or law for this repetition of a digits inside of this decimal presentation of a number e. By this quick review about the Euler number, I want to define the logarithm of a number a in a base of b. The logarithm of a in a base b is equal to c, is equal to the value c if and only if you just take a look on this expression, you can start it by putting one arrow, starting an arrow from the basis to the number c and reach to the a. Means that it's equal to, this type of the statement is equivalent to say that b to the power of c is equal to a. So the logarithm of a in a base b is equal to c if and only if that the b to the power of c is equal to a. If you just consider one circle over here, then you can calculate the value of a logarithm. So let us take a look at some example about this situation. For instance, if we have log of 4 in a base 2, then means that we are looking for some number that 2 to the power of that number is equal to 4. So this number, as you can guess easily over here, should be equal to 2. Means that 2 to the power of 2 is equal to 4. So log of 4 in a base 2 is equal to 2 as well. So by the another word, logarithm determine the exponent of that basis, the exponent of the basis, such that the base to the power of that exponent will be equal to the number 4, for instance, over here. Let us take a look at some more example here. So I put some example about the situation for the logarithm, and let us solve them one by one. So log of 8 in a base 2 means that 2 to the power of which number will be equal to 8. If you want to guess that number, it's very easy. 2 to the power of 3 or 2 cube is equal to 8. So log of 8 in a base 2 will be equal to 3. Again, log of 16 in a base of 2 should be evaluated here, and you know that 2 to the power of 4 will be equal to 16. So log of 16 in a base 2 is equal to 4. For the next example, log of 1000 to the in a base of 10, you should consider the number that 10 to the power of that is equal to 1000. We know that 10 to the power of 3 is equal to 10 times 10 times 10, means that 3 times you multiply 10 by itself. So by the another word, we know that the 10 cube is equal to 1000. So because of that, you can rewrite that logarithm as follow. You can see that log of 1000 in a base 10 should be equal to 3, because 10 cube is equal to 1000. For 9, we have log of 9 in a base 3, we have a value of 2, because we know that 3 squared is equal to 9. So the next case is a bit more complicated than the previous one. We have log of 1 over 4 in a base 2. So you know that if we have a negative, if we have the fraction like 1 over 4, we can inverse the number with the negative exponent. Means that we can write it as a 4 to the power of minus 1. 1 over 4 can be written as 4 to the power of minus 1. And moreover, we have this situation over here that 4 can be rewritten as 2 to the power of 2. So I can rewrite that one as log of 2 squared to the power of minus 1. 2 squared to the power of minus 1. And you remember from the property of exponent, if you have 2 exponents, you can rewrite that one as log of 2 to the power of minus 2. 2 to the power of minus 2 in a base 2. So of course right now we found the exponent as well, and the exponent over here can be rewritten as minus 2. So the result of this one is equal to minus 2. So you should care about that one. The value of the logarithm can be negative, as you can see over here. When we have a fraction, the value is negative, but you are not allowed to put a negative number over here or a negative number at the bases, and also the bases cannot be equal to 1, otherwise 1 to the power of each number will be 1 and you cannot calculate it. So for logarithm of 1/16 in a base 2 we have the similar situation as well, means that we can rewrite that one as some value like this. I mean 1/16 can be written as log of instead of 16 you can rewrite that one as 2 to the power of 4, and because it's at the denominator you can simply shift it to the numerator. Then we have log of 2 to the power of minus 4 in a base of 2, and the result should be equal to minus 4, as you can see over here. So because 2 to the power of minus 4 will be 2 to the power of minus 4, or 1/16. So the next logarithm that we have it over here is log of 0.01 in a base of 10. 0.01 is as the same as 1/100. So you can rewrite that one as 1/100 in a base of 10. And 100 can be written as a 10 square. So you can rewrite that one as a log of 1/10 square. 1/10 square in a base of 10, and it's resulted to 10 to the power of minus 2. So the answer of that one is minus 2, because 10 to the power of minus 2 can be written as 1/10 square. The next case is a root, and you remember the property of a root. Roots can be written as a fractional exponent. You should keep the exponent of the number for itself, means that you can rewrite that one 2 to the power of 1, and in the denominator of the exponent you should consider the roots over there, and it's a square root, it's a second root, so you can write it like this, and at the end of the day the result will be half. We can have more example about the roots as well. So we put two examples over here. Let us take a look at these two examples. So we have log of 4, the cube roots, the third root of 4 in a base 2. So again you can rewrite that expression as follow. The logarithm is in this place, so we will write the logarithm. The basis is as the same, and instead of that number 4, we keep the exponent of that one for itself, means that it's 1, and we put the denominator as 3. Then the roots converted to the fractional exponent. So moreover, the 4 over there can be written as 2 square. So I can rewrite it as a 2 square to the power of 1/3. And as you can see over here, when we have the exponent and 2 times we apply the exponent for a digit, then you can multiply that exponent together, means that it will be 2 to the power of 2/3 in a base 2. So by that things we can see that the result of that one is 2/3. For moreover, the most difficult case is a case like this, that we have the fraction and roots together in one case. So over here, to calculate the given cases, first of all we convert the roots to the forms of exponent, means that it will be 1/9 is a number that we have it under the roots, and the exponent of 9 is 1, so we keep that 1 and we put the denominator as a roots that we have it over there, and the roots is 7, so it will be 1/7. Moreover, we can rewrite that 9 as a 3 square, so because of that we can rewrite that terms as 3 square to the power of 1/7. So this will be a value like this, and right now the exponent can multiply it by itself, then we have log of 1 over 3 to the power of 2 over 7. So right now we keep the exponent over here and we multiply it by the case that we have it. So the terms is under actually division. We have 1 over 3 to the power of 2 over 7. To just inverse that number and keep that number up, we just write it as 3 to the power of minus 2 over 7. Right now we have everything's in a good situation, so the result is minus 2 over 7, as you can see over here. There are a lot of examples for that logarithm. We are not go deeply inside of it. We try to just have a quick review about the logarithm. Now let us take a look at the rules for the logarithm. So I just write 6 properties of a logarithm. However, these properties are more than this, and we can actually extend that type of the concept. This logarithm was used too much for the sailor and the people who just ride the ships on oceans. So it's important for them to calculate the value by using the logarithm. Anyway, we have some convention at the first part. If the logarithm of x is given in a base of 10, without mentioning, we just write it as a logarithm of x. It's no need to write the bases. If the bases is not written, means that the base is 10. And logarithm of x in a base e, then Euler number, it should be written as ln of x. Means that ln x is a logarithm of x in a base of Euler number. The second property said that the logarithm of a plus logarithm of b should be equal to logarithm of a times b if their bases are the same. So these properties can be easily found by the definition. Means that for example, in this case I just show this one over here. This one determined that the exponent of the multiplication is as the same as addition of the exponent. So if I consider the first term as m, if you just consider the first term as m and the second terms as n, then by the definition you can find out that over here, let me just keep the remains and put this equality somewhere else and then write that part as well. So let us take a look over here. If we consider this one over here and keep the definition of the logarithm as well, then you can see that this is the immediate consequence of the definition. So by that definition we realize that c to the power of m is equal to c to the power of m is equal to capital A, because the expression is equal to m. And for the second one we realize that c to the power of n is equal to capital B. Right now if I multiply these two terms, then you can see that c to the power of m times c to the power of n is equal to a times b. And because the bases of that multiplication are the same and their exponent is different, so I can rewrite it as c to the power of m plus n is equal to a times b. And by the definition again we can convert the situation and find the formula. Means that just replace over here the definition, means that rewrite that expression in a logarithm form again. So it seems that logarithm of c to the power of m plus n should be equal to a times b. So I just rewrite it over here, just use this definition and rewrite it. C to the power of m plus n is equal to a times b, and right now m plus n is as the same as this addition. We just evaluate that relation over here by using these properties. So let us return back to our discussion again. If we have a subtraction, then the result will be log of a over b. and for logarithm of x to the power of k, we have that k can comes out from the logarithm. This type of the property are used severally when we have the derivative of the exponent. It helps us to simplify that type of the calculation indeed. So as we have the another property that if we have log of a in a base b, then we can rewrite it as one fraction that we have log of a in any base c over log of b in any in the same base c, especially if we use the natural logarithm or logarithm with the base of e, then it will be ln a over ln b. Means that if we have log of a in a base b, we can rewrite it as this one, and this is a to the power of log of b in a base a is as the same as b. So it's again coming from this property. Just replace this c with the value of log of a in a base b over here in this expression, and you can find the property 6 as well. So this is the properties of the logarithm that can be helpful for us. Let us take a look at one example to see that how it's working. So we have one classical example about the logarithm that is as follows. We want to find the value of x for the given equation. So since the basis of this logarithm is not given, means that the basis is 10 and we have the addition of two logarithm, and based on a property of logarithm we can rewrite that expression as follow. We can keep the basis as 10 and multiply x minus 1 by x plus 1, and if you just calculate that expression, the result will be x minus 1 times x plus 1 is equal to 2. So over here we use the conjugate state, and the conjugate state said that x minus 1 times x plus 1 is equal to x squared minus 1 squared, or the result is as follows. So we have x squared minus 1 in a base 10 is equal to 2, and right now we use the definition of logarithm to calculate this expression. Indeed, you can see that the basis to the power of given number should be equal to x squared minus 1. So if you just follow the arrow over there, then you can write the expression as x squared minus 1 is equal to 100, and this will give you one quadratic equation. If you just shift 1 to the right side, then x squared will be 101, x squared will be 101, and right now by taking the roots from both sides you can find the value of x. Means that x should be equal to plus and minus roots of 101. Care about the plus and minus over here. For quadratic equation you should have two real value answer, and the delta is positive over here. We have two answer. One of them is 101 roots of 101, and the another one is minus roots of 101. So the positive one is we can use the positive roots, but for the negative roots you should care about the logarithm of x minus 1. This make the first logarithm negative, so the second answer is not acceptable. The only answer will be plus roots of 101. However, we can discuss about the several types of this examples. For instance, we have the example of writing the logarithm in terms of the another one as well, but we need only that much of the information about the logarithm. At the end of this lecture we will discuss about some statements, some important statement, the Newton expansion, and some important statement, and I think that we should talk about the trigonometric function in the next lecture. So at this time, let us take a look at some important identities that are coming for the algebraic expression. The first identity that you can see over here is an identity that we call it the conjugate state. So means that if you have x minus a multiplied by x plus a, then the result will be x squared minus a squared. Over here we have x and a in a common in both expression, and we have negative and positive cases. These two terms means that x minus a and x plus a are called the conjugate of each other, means that x minus a is a conjugate of x plus a, and so on. So this type of the expression can be extended to x to the power of n minus a to the power of n as well, means that we have this extension of this algebraic expression. Later on we will discuss about these things as well. The second relation that you can see over here said that x plus a to the power of 2, or x plus a square, will be the first one square plus 2 times of the first times second plus second one square. It's a binomial expansion indeed, and if we have a negative sign, for sure x minus a square will be x squared minus 2 times of the first times second plus second one square. If you replace minus a instead of a in the first one, then you can reach to the second expression. Generally this type of the expansion can be seen in a Pascal triangle. Let us take a look at the Pascal triangle. It's not a bad idea to have some review about that things. If you have a triangle as follow, that you put one at the top and one in the side of each one, and then add these two value to get 2 in the middle, and again 1 at the edge of this triangle over here, and again add them to reach to the same to the next number, means that 2 plus 1 is 3, and again 2 plus 1 should be added to get 3. Then you have a Pascal triangle. So in a Pascal triangle, if you just take a look on it, it's determine the coefficient of a plus b to the power of n, means that at the first part, that one determine a plus b to the power of 0, means that at the top it's determine a plus b to the power of 0. Next one determine the coefficient of a plus 1 to the power of 1. If we have a plus b to the power of 1, then the result will be 1 times a plus 1 times b. And for the next one, if we have a plus b square, so if you have a plus b square, like the case that we talk about it at the at top, then it will be 1 times a squared. Then you should reduce the exponent of a 1 times, then it will be 2 times of a. I reduce the exponent of a squared becomes a, and I add the exponent to b, so 2 times ab. And the next one, again, if I reduce the exponent of a, it will be a to the power of 0 or 1, and then b a square. We decrease the exponent of a and increase the exponent of b step by step. So as you can see, we have this expression over here, and by the Pascal triangle you can find the coefficient of a plus b to the power of n. Generally, Newton discovered that the a plus b to the power of n can be written as a combination of 0 out of n a to the power of n, 1 out of n a to the power of n minus 1b, and so on. And this combination has a meaning of follow, means that we have this interpretation for the combination. The combination of k choose out of n is n factorial over k factorial times n minus k factorial. By the another word, this 0 chosen out of n can be written as n factorial over 0 factorial times n minus 0 factorial. And for the remaining case also we have the following expression. So this is the Newton expansion, and without using this Pascal triangle, you can find the coefficient by using that combinations. So it's not a bad idea to just memorize the a plus b square and a plus b cube in your mind. The remainder is not that much practical. So let us return back to that cases. If we have x plus a times x plus b, means that if x is in a common but we have two different cases like a and b over there, then the result will be the common terms square or x square plus the uncommon terms, the addition of uncommon terms times the common terms, means that a plus b times x plus the multiplication of uncommon terms. So it can be helpful when you want to solve one quadratic equation. For instance, when we have x squared, for example, if you have x squared minus 3x plus 2, then to calculate the quadratic equation, instead of using the delta formula, we can rewrite them by the multiplication of two expressions that x is in a lead. So right now we are looking for two numbers that their addition is minus 3 and their multiplication is 2, means that the addition a plus b is equal to minus 3 and the multiplication of that two number is a times b. Equal to 2. So if you just take a look at the number 2, the multiplication of 2 and 1 is 2, and also minus 2 times minus 1 is 2. So we can simply replace it by minus 2 and minus 1, because right now the addition of minus 2 and minus 1 is minus 3 and the multiplication of minus 2 and minus 1 is 2. So we found the roots without using the delta formula right now, because if I just make it equal to 0, then x could be equal to 2 or x is equal to 1. We found the roots of this quadratic equation without using the delta formula. For the next case as well, it also can be considered as a expansion of the conjugate state. So for finding this expansion, it's easy to calculate it by using the long division. What do I mean? For example, let me just calculate the long division for this case that we have x4 minus, for example, 16. If we have x4 minus 16, or we can rewrite that one as x4 minus 2 to the power of 4, then to calculate that one, you can use a long division and divide this x4 minus 2 to the power of 4 or 16 by x minus 2. So let us use the long division and divide that terms by x minus 2. Right now, to calculate the x4 minus 16 over x minus 2, I'm looking for the biggest or greatest exponent, which is x4 here, and the biggest exponent here is x. So this long division is useful to calculating the limit sometimes. So it's not a bad idea to learn how to use the long division for the algebraic expression. The greatest exponent is x4, and I should divide it by the greatest exponent of a divisor, which is x. And if I divide x4 by x, the result will be x cubed. So I will write x cubed over here now, and then I multiply this x cubed by the given terms, means that x minus 2. If I multiply by that one, then I have x3 times x4, which is x4, x3 by x, which is x4, minus 2 times of x cubed. Right now, to add these two terms, I should change the sign of the expression. Means that this negative change to the positive and this positive change to the negative. After I add them together, this greatest exponent will be cancelled, and the result over here will be 2x cubed minus 16. So to calculate, to continue our long division, we do the similar things. Means that right now the biggest exponent is 2x cubed, the biggest terms over there, and I should divide it by the biggest exponent of divisor, which is x. So the result is 2x squared. I should put over here 2x squared then. If I put 2x squared at this stage, then I should multiply 2x squared by x minus 3 again. The result will be 2x cubed and plus 2x squared times minus 2 is minus 4x squared. And again, I should change the sign and add them together. So if I change the sign, this one becomes plus, this one becomes minus, and these terms will be cancelled. The result is 4x squared minus 16. So we should continue our calculation because still the exponent is bigger than x. So in the next step, I should use the division again. And 4x squared, the biggest terms over here, divided by the biggest term, which is x here, give us the 4x. So if I multiply 4x by the given terms x minus 2, then I have 4x squared. And for the second one, we have minus 8x. So again, I should change the sign, and if I change the sign to the negative one, then 4x squared will be cancelled with 4 squared at the bottom. The result is 8x minus 16. And I should continue this calculation and put the terms over here, means that I have 8 right now. If I multiply this one by 8, then I have 8x minus 16. And again, I should change the sign, and if I change the sign over here, then the result will be 0. The remainder over here is 0. When it's 0 means that it's divisible by x minus 2. So I can rewrite that one as x minus 2, the divisor, multiplied by the terms that we find it over there, means that x cubed plus 2x squared plus 2x squared plus 4x plus 8. So you can find the expression by the division as I said it, and as you can see over here, it's as the same as the expansion that we talk about. It means that x to the power of 4 minus 2 to the power of 4 will be x minus 2 without the exponent, without this exponent. I will rewrite it over here, x minus 2. Then I start to write it by the one lower exponent. Lower than 4 is 3. So I started by x to the power of 3. Then I will write 2, the next term, to the power of 1, and I reduce the exponent of x cubed to x squared. I decrease the exponent of x and increase the exponent of 2. So first one is 2 to the power of 1, second one is 2 to the power of 2 or 4, and I reduce the exponent of x, and in the next step at the end I have 2 cubed or 8. So in this way we can calculate the long division as well. So I will finish our lecture at this point, and later on we will continue our discussion with the trigonometric function and their properties as well. Thank you for your attending.